Testing. 1 2 3. 1 2 3. 1 2 3. 1 2 3. Ooh. Yep, we are so back. Okay, we are so back. Currently it is the 9th January. It's a Friday. Ooh, Friday. So weekend is here, almost. When I get home, and it's been sipping on some creatine. So I'm gonna go training or working out after this stream. And today's stream is gonna be a chill one, just like chill, read new topics, study stream, basically. So yeah, I watched the old stream. It was a complete mad show. Like, there was so much going on, and like the camera couldn't keep up with my awesomeness. It was hell, bro. Now I kind of fixed some issues, like it doesn't flicker, like all the weird stuff appearing, and it also looks a bit smoother. Yeah, it also looked a bit smoother than before, and hopefully no lags this stream. But yeah, again, I just started this streaming thing, and yeah, so many issues I have to solve, man. Absolute devastated. So yeah. Yeah, so let's just get started. And it also, what the, okay, so it says it skipped frames or something. Anyway, we're gonna go to our I also got this, this right here. This right here. That's pretty, like, professional, I guess. Okay, so I'm gonna do this. Yep. And we're gonna be talking about electrophilic aromatic substitution. And yeah, so I'll just read a bit. You can see the whole thing, right? Yep, yeah, okay. So, let me check if everything is working. Okay. We must begin this chapter with a review of reaction from the first semester of organic chemistry. Recall the addition of bromine, Br2, across a double bond. So as you can see here, we have a cycloalkene reacting with bromine, which then turns it into a anti reaction with enantiomer. Okay, and when we learned this reaction in the first semester, we saw that this reaction involves a nucleophile attacking an electrophile. The nucleophile is the double bond, and the electrophile is bromine. To understand how a double bond can function as a nucleophile, recall that the double bond results from the overlap of two neighboring p orbitals, each with one electron. So it looks like this. Therefore, a double bond represents a region in space of high electron density. Even though there is no full negative charge anywhere, the double bond can function as a nucleophile and can attack an electrophile. A nucleophile is basically an atom that is electron rich. and electrophile is the atom that is or compound that is electron poor. But the obvious question is, why is bromine an electrophile? After all, the bond between the two bromine atoms is covalent, and therefore we cannot say that one of the bromine atoms has any more electron density than the other. There is no induction here because both atoms, bromine and bromine, bromine and bromine basically, have the same electronegativity. There is a simple reason why bromine can act as an electrophile here. We need to consider what happens when a molecule of Br2 approaches an alkene. To help us see this, think of bromine in terms of the electron cloud surrounding it. So we have like an illustration here. As the molecule bromine gets close to the pi bond of an alkene, the electron density of the pi bond begins to repel the electron cloud around bromine. This effect gives the bromine molecule an induced dipole moment. This is temporary interaction. It only happens while the bromine molecule is near the alkene. So we have an electron-rich alkene, which can attack the nearby electron-poor bromine atom. This gives the reaction that we saw in the first semester of organic chemistry. So we have seen, or I have seen this in the first semester of my organic chemistry course. So one of my plan was to to create some like series, organic chemistry series, like to help people that is finding organic chemistry hard, like some small videos to help with organic chemistry easy. Yeah, so I'll think of that in the future. I'll be uploading like a playlist that you guys can access and see how easy and good tricks to do in organic chemistry. Okay, so okay, now let's consider what happens if we try to do this exact same reaction with benzene as a nucleophile. So we're trying to perform this reaction. So we have a benzene here and bromine that reacts with benzene, which becomes this. But when we use bromine to benzene, there is no reaction. So how the hell can this even be a thing? We can understand this because benzene is an aromatic compound. It has a special stability due to its aromaticity. If we add bromine across benzene, aromaticity will be lost, and that is why the reaction does not take place. It will be going uphill in energy, but is it possible to try to force the reaction to happen? This brings us to a simple and important concept in organic chemistry. One of the driving forces for any reaction between a nucleophile and an electrophile is the difference in electron density between those two compounds. The nucleophile is electron rich and the electrophile is electron poor. Therefore, they are attracted to each other in space. So opposite charges attract. So if the reaction is not proceeding, we can try to force it along by making the attraction even stronger between the nucleophile and the electrophile. We can accomplish this in one of two ways. We can either make the nucleophile even more electron rich, so more nucleophilic, or we can make the electrophile more electron poor, so more electrophilic. So, okay, in this chapter we will explore both of these scenarios. For now, let us start by trying to make the electrophile a better electrophile. How do we make bromine a better electrophile? Let's remember why bromine is an electrophile in the first place. Just a few moments ago, we saw that an induced dipole moment is formed when bromine gets close to an alkene. This creates a partial positive charge on one of the bromine atoms. Clearly, if we had Br plus instead of bromine, that will be an even better electrophile. We will not have to wait around for bromine to become slightly polarized. But how do we form Br plus? That's where Lewis acid comes to picture. Okay, so something about Lewis acids. Okay, consider the compound AlBr3. The central atom in this structure is aluminum. Aluminum is in column 3A of the periodic table, and therefore it has 3 valence electrons. It uses each of these electrons to form a bond, which is why we see 3 bonds to the aluminum atom in aluminum AlBr3. So this is how the Lewis structure of AlBr3 looks like. But you should notice that the aluminum atom does not have an octet. If you count the electrons around the aluminum atom, there are only 6 electrons. That means the aluminum has one empty orbital. That empty orbital is able to accept electrons. In fact, it will exhibit a tendency to accept electrons because that will give aluminum an octet of electrons. Therefore, we call AlBr3 a Lewis acid. To put it simply, Lewis acids are just compounds that can accept electrons. Another common Lewis acid is iron Br3. Okay. So with the Lewis base, it attacks iron, which then makes sense. Now let's consider what happens when bromine is treated with a Lewis acid such as LlB3. The Lewis acid can accept electrons from Br3 to Br2 bromine. So we have AlBr3 that reacts with bromine. Bromine attacks then the empty orbital that is in aluminum, which then gets connected or reacted. The resulting complex can then serve as a source of Br plus like this. Okay, so after we create this product, then the bond between the bromine hops to the other bromine, the plus charge, which then takes the other bromide away, which makes them plus. So that's how you make Br plus. It is probably not accurate to think of this as a free Br plus that can exist in a solution by itself. Rather, the complex can transfer Br plus to an attacking nucleophile. Okay, so yeah, the nucleophile attacks the bromine attacks the hops to bromine, which then becomes like Br. Okay. The important point is that this complex can function as a delivery agent of Br plus, and that is what we need in order to force a reaction between benzene and bromine. So let's try our reaction again. When we treat benzene with bromine in the presence of a Lewis acid such as AlBr3, a reaction is indeed observed, but it is not the reaction that we expected. So in the previous one, it gave us a syn addition of bromine, which in this case it doesn't. So this is not an addition reaction, rather it is a substitution reaction. One of the aromatic protons was replaced with bromine. Since the ring is being treated with the electrophile, which is Br plus, we call this reaction an electrophilic aromatic substitution. To see how this reaction occurs, let's take a close look at the accepted mechanism. It is absolutely critical that you fully understand this mechanism, because we will soon see that all electrophilic aromatic substitution reactions follow a similar mechanism. The first step shows the ring acting as a nucleophile to attack the complex, thereby transferring Br plus to an aromatic ring. Okay, so the benzene is the nucleophile, and this is the electrophile. So the benzene attacks the bromine, and then the bromine hops to the plus charge, which then it created this product. Okay, it is important to this step generates an intermediate that is not aromatic. It is true that aromaticity has been temporarily destroyed, but it will soon be re-established in the second step, the final step of the mechanism. In this first step of the mechanism shown above, the ring attacks Br plus to form an intermediate that has 3 resonance structures. Okay, so the resonance is it hops to the plus charge here, hops to the plus charge here, and then it gets created the intermediate. It is important to remember what resonance structure represent. Recall from the first semester that resonance is not a molecule flipping back and forth between different states. Rather, resonance is a way we deal with. Okay. Yep. So it's just doing resonance. Okay, so it's called for sigma complex, the resonant part. The second step, last step of the mechanism, involves deprotonation to reform aromaticity. Okay, so a base attacks the proton hops to the plus charge, which creates this. Notice that the proton is removed by a base. Technically, it is not correct to just let a proton fall off to space by itself like this. Yeah, that's just wrong. Okay, so whenever you're drawing a deprotonation step, you should show the base that it's removing the proton. In this particular case, it might be tempting to use bromide to remove the proton. But bromide is not a good base. The first semester, we learned that the difference between basicity and nucleophilicity, and we saw that bromide is a very good nucleophile, but a very poor base. Instead, aluminum tetrabromide functioned as the base that removes the proton. I need some water. Notice the aluminum tetrabromide functioned as a delivery agent of bromide. Okay, so we have aluminum tetrabromide here. The bond attacks the proton, which then hops to the positive charge, which then creates these products. In the end, the Lewis acid aluminum tribromide is regenerated, so the Lewis acid is actually not being consumed by the reaction. It is only there to help the reaction along, which is why we call it a catalyst in this case. That is why the presence of even a small quantity of Lewis acid will suffice. Now that we've seen both steps of the mechanism, let's take a close look at the mechanism all once. Okay, so I have to remember that when I see this thing in the exam set, it's a catalyst. Its role is a catalyst. Okay. So we have the whole mechanism. This takes that. This take this. Alright. Yep. And then it creates the sigma complex with resonance. And then the base reacts to the proton, which then creates this. Okay. On the surface, it might seem like many steps. However, remember, the resonance structures are not actually steps. Those three resonance structures are necessary so that we can understand the nature of the one and only intermediate, the sigma complex. Indeed, the mechanism has only two steps. In the first steps, benzene acts as a nucleophile attacking Br plus to form the sigma complex, and in the second step, a proton is removed from the ring to re-establish aromaticity. In summary, the two steps are attack, then deprotonate, and to put it in other terms, Br plus comes on, and then H plus comes off. That's all there. Yeah, so it seems pretty simple mechanism, nothing too bad. Yeah, so I'm gonna do this problem on my iPad. I don't think I can share it though because it can't connect to the internet. My iPad, it's because it's very weird, I guess. So I'm gonna do this problem 4.2, and I will show you what I did. Give me a moment. Okay, so we have this one. Okay, so we have a benzene ring. It attacks the chloride, then hops to the positive charge, just like with bromine, but this time with chloride. Then the sigma complex. Yep, sigma complex. The resonance stuff. So it just hops to this one. Then it hops this one. Okay, and then this reacts as a base which attacks the proton, and the proton then gets to the positive charge, and then we get the product. Simple. What time is it? Yeah, okay. 2 p.m. Go join benzenes. Okay. So basically it's like this. Oh, that works pretty well. So the benzene attacks this compound. Wait, zoom in for you guys. Yeah, so the benzene attacks this product, this compound, and then we created chloride plus, and then the sigma complex resonance, this hops there, the other one hops there, and yeah, so aluminum trichloride attacks the proton, which is a base now, attacks the proton, and the proton gets to the positive charge, which then gives us this product right there. That's the whole mechanism, which was the assignment. Let me check. Yeah, so we literally got that, so it's basically correct. And yeah, so that was a pretty easy task. We just need to like figure out the like, what is it called? There's like a blueprint of every mechanism. Okay. Okay. So in the next one, we have nitration. Now, what the hell is nitration? Nitration. In the previous section, we saw that the mechanism of electrophilic aromatic substitution reaction. We saw that the mechanism is the same whether you are installing Br+, Cl+, or iodine plus on the ring, just like I did. We also said that this same mechanism explains how any electrophile E+ can be installed on an aromatic ring. For example, let's say we wanted to convert benzene into nitrobenzene. Okay, so instead of chloride, you do it a nitrobenzene, apparently. In order to form nitrobenzene, give me a moment. In order to form nitrobenzene, we need NO2+ as a electrophile. But how do we make NO2+? If you look how we made Br+ or Cl+ in the previous section, we might be tempted to use NO2Br, nitrobromide, and aluminum tribromide to get the following complex. Okay, so the NO2Br attacks the aluminum tribromide, which then creates this complex, and the nitro group then gets away, jumps ships, and then okay, so we get, oh, that's pretty easy if we want okay. This complex could serve as a source of NO2+. The problem is that NO2Br is nasty stuff, and you probably would not want to work it with a lab, especially since there is so much simpler way to make NO2+. Oh shit, okay. We can form NO2+ by mixing sulfuric acid with nitric acid. Okay, so we have nitric acid and sulfuric acid react with benzene, which gives us this product. Fine. We need to take a close look at how NO2+ is formed under these conditions. Let's begin by drawing the structures of sulfuric acid and nitric acid. Okay, that's the liquid structure of the both. Fine. Yep. Notice that the nitric acid exhibits charge separation. It might be tempting to remove the charges and draw it like this. Oh hell no. Yeah, don't do that, because nitrogen doesn't have nitrogen can't have 5 bonds, can they? No. But you cannot do that because it will give 5 bonds to the central nitrogen atom. Nitrogen can not ever have 5. Oh, I just said it. Because it only has 4 orbitals that it can use to form bonds. So nitric acid must be drawn with the charge separation. Alright. Now that we have seen the structures of both nitric acid and sulfuric acid, we must remember that the term acidic is a relative term. It is true that nitric acid is acidic, and it is also true that sulfuric acid is acidic, but between those two of them, sulfuric acid is stronger acid. It's a stronger acid. In fact, it is so much stronger as an acid that it's able to give a proton to nitric acid. Okay, so sulfuric acid is a strong acid, so it can give a proton to nitric acid. That's right. It might seem weird because nitric acid is essentially functioning as a base to remove a proton from sulfuric acid. And it might make us uncomfortable to use nitric acid as a base. But that is exactly what is happening. Oh, my throat. Oh, why? Because relative to sulfuric acid, nitric acid is a base. It's all relative. Okay, so nitric acid removes a proton from sulfuric acid. But the obvious question is, why does the uncharged oxygen remove the proton? Wouldn't it make more sense for the negatively wouldn't it make sense for the negatively charged oxygen to remove the proton like this? Whoa, I stumbled on that word. Okay. The answer is yes, this probably would make more sense, and it probably happens like this a lot more often. The oxygen with the negative charge probably removes the proton much more readily than the uncharged oxygen atom does. However, proton transfers are reversible. Protons are being transferred back and forth all the time, and all of this happening is very quickly. So it is true that the negatively charged oxygen atom removes the proton more often. But when that happens, the only thing that can happen next is the proton to be given right back to reform nitric acid. Every once in a while, however, the uncharged oxygen atom can remove the proton. And when that happens, something new can happen. Next, water can leave. Okay, so there's basically an aqueous solution, since water is present. So yeah. So when this happens, NO2 plus is generated. So when we mix sulfuric acid and nitric acid, we get a little bit of NO2 plus in the equilibrium mixture, and that NO2 plus functions as an electrophile we need to in order to install a nitrogen tube. Okay. Once again, the following mechanism is essentially the same mechanism as we saw in the previous. Yeah. So basically, nucleophile attacks electrophile. This hops there, and the sigma complex resonance, and then water attacks the hydrogen instead of a base. But this in this reaction, water can function as a base since it's a amphibolite. Isn't like that the word? I don't know. Yeah. So this attacks the proton and this attacks the charged spot, which gives us this. In this case, we're using water to remove the proton instead of aluminum Br4 minus, which will make sense because we don't have any in this reaction. There's plenty of water because, like I said, because nitric and sulfuric acid are both in aqueous solution. Like I also said, notice that the mechanism is very similar to what we have always seen in previous reactions. So far, we have seen how to install a halogen ClBrI on a aromatic ring, and we have seen how to install a nitro group. Before we move on, let's just make you a favor, blah 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 blah. Okay. Yeah, so this is 4 5. We react to get this product. We have to use Br2 and aluminum 3 bromide, and in that's nitric acid and sulfuric acid. So HNO3 and H2SO4, and in here we need Cl2 and AlCl3. Let me draw it for you real quick what I mean. Okay, so this reacts with yep. Yep. Nitric acid and sulfuric acid gives us a nitrobenzene. Yep. Okay, so I basically drew this. You see that? So the first one, it reacts with bromide. It gives us this. This gives us this one, the nitro we just learned, and this one gives us this one. So yeah, I think I got it. Thank you, book. Yeah. So the next chapter is about Friedel-Crafts alkylation and acylation. Sounds very okay. I wanna like explain a bit next time. Whoa, what happened? Okay, never mind. So I wanna explain like read that next time. The time is currently what, 3 p.m. I haven't even eaten yet, so I have to eat also. And yeah, so it was a good topic, small one. Electrophilic aromatic substitution. Pretty interesting. Not that difficult of mechanism, in my opinion. It's like just a formula to follow, and all the other mechanism is like that. So when you're talking about electrophilic aromatic substitution, yeah, that's the word. But yeah, it's gonna be a short stream, I guess, but it was fun. I'm glad I fixed my camera finally and all the lag bullshit that was. And yeah. So yeah, there's nothing else much to say. Cheers. I'll see you tomorrow. Or not. Tomorrow. I'll see you next time. Goodbye. How the hell do I end this shit?